So thank you very much for the invitation to come here and have the chance to present a solar physicist's very simplistic view on vortices and applications of the Liutex in solar and stellar atmospheres. This is a work, there is still some echo going on, no? Nope. Which is, okay, good. Or maybe there is some other microphone being open. I don't know. Okay. No, seems not to be the case. Okay. No, I have the microphone. I just thought there is another microphone open that makes kind of, maybe this one. Yes. Oh, this one is off. Okay. Okay. Good, fine. Yes, now it's, I think it's better. So this work has been carried out mainly by a PhD student, actually José Roberto Canivete Quisa at the Istituto Ricerche Solari in Locarno. Roberto is now doing artificial intelligence in a private enterprise, so he can no more report about this. So we know about the vertical motions in the Earth's atmosphere, of course, in the forms of typhoons or hurricanes or tornadoes. And likewise, there are vertical motions also in planetary atmospheres. Here, this very nice on the left-hand side, a very nice vertical system at the south pole of Jupiter, and on the right-hand side another vortex in Jupiter's atmosphere. And so there is maybe not so a surprise that also in the solar atmosphere we have vertical motions, but they are a bit hidden in a granular pattern, we call that. These granules are material that flows out. The sun cools off and it flows down in these dark intergranular lanes. And this bright stuff here, of that we know these are concentrations of magnetic fields. And especially when you follow these small-scale magnetic fields, you see sometimes, like here, that they move on a spiral pattern. And obviously they are caught in a vortex motion, and so that's a way how to discover, how to see vertical motions in the solar atmosphere. This has been done by Bonnet and collaborators in 2008, and meanwhile there is a whole list of papers that have observed such vertical motions in the solar atmosphere. Actually, what we see here, this is the visible surface of the sun. This is what we call the photosphere. Now, likewise, when we go higher up, 1,000 kilometers higher up in the solar atmosphere, we come into the chromosphere, and there again, you see these typhoon-like objects here, and right beneath them, here in the photosphere, we see these bright features again, and these are magnetic fields. So obviously, these vertical motions up in the chromosphere, they have to do typically with magnetic fields. And likewise, again, there are a whole bunch of papers, meanwhile, they have observed these vertical motions in the chromosphere. Now I would like to move to simulations. On the left-hand side, we have again an observation of granules. You see, by the way, you see down here the state of Texas. So a granule has the size typically of the state of Texas. And here we solve the system of magnetohydrodynamic equations together with radiative transfer. And it shows you that it is pretty similar down to small details of the magnetic field to what is observed on the sun. So we can now pretty good reproduce at least what happens in the photosphere of the sun. And I can quickly try to show this movie here, although I saw before it doesn't move, it doesn't play very smoothly because it goes over the internet. And let's try again. Then you see on the right-hand side, it moves quite good, you see the chromosphere, and you see whenever there is a circle, a very nice, typhoon-like swirl, the way we have seen it in observations. And on the left-hand side, we are deeper down in the photosphere, and there you always see, when there is a swirl, you see a bright feature of which we know these are magnetic flux concentrations. Now you can put a line of sight along spirals, and you can plot along this line of sight, say the vorticity, or better, the swirling strength, and do that in time. And then you get plots like this one, which we call a time distance diagram. Distance is high from zero photosphere to up into the chromosphere. It moves. Then we see here that here what I plot is the swirling strength, and we see that there are ridges that obviously is its swirling motion that propagates upwards. And this green dotted line would be a hypothetical particle that moves with the Alfvén speed plus bulk speed. The Alfvén speed is the characteristic speed in magnetohydrodynamics. And the red line would be when it moves with the speed of sound. So obviously this swirl moves with the Alfvén speed. And likewise, we can also compute the swirling strength of the magnetic field, which is a measure of twist. And we see, not so clearly, but also such a ridge with the same velocity propagating upward and of opposite sign. And both the fact that it moves with Alfvén speed and has a phase relation 180 degrees between velocity and magnetic field suggests that this is a torsional Alfvén waves that moves along magnetic field in the upward direction. Here is a plot of the gray. This would be the solar surface. Green is our streamlines, and this shows the vorticity. And of course, we know now the vorticity includes a lot of shearing and not only rotation. And when we plot then the swirling strength, we have a nice vortex tube. Also here in the background, there are several vortex tubes which are not clearly visible in the vorticity. So the swirling strength is, of course, a much better quantity. Now, my view, simplistic view of the swirling strength is it derives from an eigenanalysis of the Jacobian of the velocity field. And whenever the flow is a little bit curved, then we can decompose that into a matrix that consists of the real eigenvalue and two complex conjugated eigenvalues. And then you see that this submatrix here is a rotation matrix, and it indicates rotation in a plane perpendicular to the real eigenvector. And the eigenvector, the real eigenvector would be the rotation axis, and the complex part of the complex conjugated eigenvalue tells you about the degree of rotation. And actually, as the swirling strength, we define 2 times the complex part of the complex conjugated eigenvalue. Why do we take this factor 2? Because then the vorticity and the swirling strengths are identical in case of rigid rotation. Now, the nice thing of vorticity is that there exists a evolution equation. You just have to take the curl of the right-hand side of the momentum equation, and then you get an expression like this, which consists then on the right-hand side of a tilting and stretching term, a baroclinic term, the magnetic baroclinic term, and the magnetic tension term. So in hydrodynamics, you have only the first 2 terms, but you would have maybe additional terms that comes from viscosity when you have a Navier-Stokes equation. But here we consider ideal magnetohydrodynamics. Now we managed to derive a equal equation for the swirling strength. This looks a little bit more complicated because it's now a tensor equation, but in principle it has the same terms. They're a baroclinic term, magnetic baroclinic term, magnetic tension term, and an additional term that comes from gravity, which we are still puzzled why it is not there for the vorticity, but it's there for the swirling strength. Anyway, what is this evolution equation good for? Well, if we go again to this time-slice diagram, we have here a sequence of two torsional Alfvén pulses that propagate upwards. Then we take of the swirling strength, or the vertical component of the swirling strength, the time derivative. Then we get the left-hand side of this equation, yeah? Then we can, for each of these terms, we can make an equal time slice diagram. And in this case, I show only the fourth term, because that is basically equivalent to the left-hand side. So it is the dominant term. And this term here tells us it's this one, the fourth, it's the magnetic tension term. And that tells us that the restoring force is magnetic tension, and this is a torsional Alfvén wave. This is finally the proof that it is a torsional Alfvén wave. So this equation is very useful for determining the mode of a wave. Now let's move to the Liutex. So the Liutex is the rigid rotational part of a vortex. And it can be, according to Wang and Xu, I think, which may be here in the audience, I'm not quite sure, it can be expressed in terms of the vorticity, the real eigenvalue, and the swirling strength. And I think we have seen this equation already 2 times maybe today, and I'm always a little bit puzzled because, you know, the square root has 2 solutions, plus and minus, and only the plus makes physically sense. But I'm kind of puzzled if this can be shown mathematically, that you have to, in principle, one would have to put here the absolute values, but we can discuss that in the coffee break, maybe. Somebody can explain me how that is. Now, if we have a rigidly rotating vortex, then vorticity, swirling strength, and Liutex are the same. And the rotational period is given by 4 pi in our definitions with the 2 times complex eigenvalue. Anyway, 4 pi divided by vorticity, or by swirling strength, or by Liutex. Now, if we go to a differentially rotating vortex, like the Lamb-Olszyn model, then the rotational period is, of course, a function of radius. Yeah? And for this analytical vortex, it is given by this gray, thick gray line. Now, when we take the vorticity and use this formula, and the vorticity is also a function of radius in this vortex, yeah? And we apply this formula, then we get this dashed line. And you see it deviates strongly from the true rotational period. If we take the swirling strength, it gets even worse. If we take the Liutex, it perfectly agrees with the correct rotational period. And we did that with other vortices, not only with the Lamb-Olszyn, with a whole bunch of, and it's always like that. Only the Liutex correctly renders the true rotational period. And this is very useful. I will come back to that in a minute. Now, real-life vortices are, of course, more complex than the rotational symmetric case of the Lamb-Olszyn vortex. Now we know this famous definition of Lucht has been shown today also. A vortex is a rotating motion of multitude of material particles around a common center. And then when I look at this definition, you know, I have the feeling a local criterion, such as the Liutex, or the vorticity, or the swirling strength, or the Q, or delta function, etc., are not, there is missing something. These are local criteria. But we need also a more global criteria, especially, of course, in these large-scale vortices on planets and on the sun, etc. So the idea was that for each point of a flow, we compute its approximate curvature center. And when we have a real vortical flow, then many curvature centers have their origin at the same place. So we get a cluster of estimated vortex centers. And that would then define the center or the center point of the vortex. And how do we do that? Now we know that the rotational period is given by 4 pi divided by the Liutex. We don't use any streaming lines. We just use the Liutex. At the same time, the rotational period is at a given radius r is of course the circumference of this circle divided by the tangential velocity. And when we look at these two equations, we obtain the curvature radius. It's simply 2 times the tangential velocity divided by the Liutex. Now we don't know the tangential velocity. Maybe somebody has a good idea. We just took there the velocity we have on a given location. And so we say, okay, the curvature radius is 2 times the velocity divided by the Liutex. That is not good enough. We also need the direction of this radius. And that can be derived pretty simple from a Taylor expansion. I cannot go now into the details, but the result is that the Jacobian, the inverse of the Jacobian applied to the velocity is proportional to the direction of the curvature radius. So we have then the curvature radius and we have the direction, and so we can go point by point through the entire velocity field and find the origin of this curvature. And then we get clusters of such origins, and then it's just a matter to find these clusters. Of course, if we plot that, we can immediately tell here is a cluster, but we have to tell the computer this. And for that, we use 2 criteria. One is the local density of estimated vortex centers. It's just the number of such points within a hypersphere. And another criterion is the spacing criterion, which finds the distance between a data point I and the next data point j with a higher local density. And then we have to apply some criteria, we say that, we take only those, we apply a threshold to the density, but this does not remove any estimated vortex center. It just gives, it just determines what can be considered a significant cluster of estimated vortex centers and what not. Likewise, for the spacing criteria, we have to make sure that the next maximum is far away, from the actual that we are looking at. So this plot here shows, for example, the this is an artificial flow. We put here 2 Lamb-Oseen vortices plus noise, quite strong noise. And then this colors shows the Liutex. Now you see the Liutex here is kind of maximum out here, which is not exactly where the Lamb-Oseen vortex has been placed. This plot here is now the estimated vortex centers, and they peak very, very sharply and close to where we have put actually the Lamb-Oseen vortex. So I think it's a better way to determine the center of the vortex than it would be otherwise. Then in this algorithm we have to add, of course, I should say here, there are some parameters involved, you know, but these parameters we have never a threshold on the Liutex, which is important because if we have a very slowly rotating vortex, then we still find a cluster of vortex centers. We do not remove any, but nevertheless, the whole algorithm has, of course, some free parameters. This is unavoidable. I cannot go here into the details. In any way, these steps take also care of situations like this, which are not vortices, which however would give a non-vanishing Liutex. But we cannot consider this or this flow a vortex, and that these steps takes also approximately care of such cases to remove them. Now here we have the situation after step 1 here. We would have this situation. We have here a vortex, but this region here would also belong to this vortex. But then, you know, the final, this second and third step would take care of these cases here which are too far away and which would treat them as noise. Anyway, we have here tested also with, in this case, with 9 Lambda-Oscine vortices that we put in plus noise, and I don't want to go into these details anymore because I'm running out of time. There is a GitHub address and Zenedo where there is a Python program of this algorithm that I just explained, and the algorithm is explained in these papers. Here we have applied then to a simulation of the solar surface. You see that these vortices appear preferentially at the border of magnetic flux concentrations. And this would be the situation higher up in the chromosphere. Then we can do that layer by layer through the solar atmosphere, and we see that there are vortex tubes that reach from the photosphere higher up into the chromosphere. So I come to my last slide and come back to this question, what is then a vortex? So in descriptive terms, you know, I come back to this definition, which of course is quite crude, but may be useful by looked. But this is of course a description. There is no mathematics behind it. A mathematical version is less straightforward, but from what I have said now, one could attempt to say a vortex is characterized by a local enhancement of the Liutex, yes, but this is true also for vorticity and for swirling strength. The vortex center is given by the peak density of estimated curvature centers, where the curvature radius and its direction are determined by the Liutex and the local velocity field. Sounds not very nice, but behind all these things are real formulas. Yeah, the Liutex and also this estimated curvature and estimated curvature centers and clusters of it, etc. So I have the feeling it's closer to a mathematical expression than the first one. Thank you very much.
Thank you very much.